All right, everyone, we're going to continue our discussion of denitrification by taking a look at some factors that affect denitrification. And in this lecture, we're going to talk about what are those factors that affect denitrification. We're going to look at how they affect denitrification, and I'm going to give you a lead-in to an example problem that you're going to have as part of this module where we look at a comparison of multiple different carbon sources that can be used for heterotrophic denitrification. So let's get rolling here. Okay, so if we remember back to our electron tower, right, we can remember that nitrate, reduction of nitrate into nitrogen gas here, is a little bit lower than reduction of oxygen into water in terms of energy, right? It still is pretty high though, and so we know, so when we're thinking about factors that impact denitrification, we might be able to understand that facultative denitrifiers might prefer to use oxygen, right? Facultative again means that they're flexible and they're able to use different kinds of electron acceptors. So if there's both oxygen and nitrate available, then these facultative denitrifiers are generally going to prefer to use oxygen over nitrate because they can obtain more energy. So that means that when we're trying to do denitrification, we need to minimize our dissolved oxygen. Because otherwise, our denitrifiers are going to prefer to use the oxygen and they're not going to do that denitrification that we want them to do. There's also some denitrification enzymes that can be inhibited at high dissolved oxygen concentrations. And typically we try to shoot to keep our dissolved oxygen at a level less than about 0.2 milligrams per liter. And if you can keep it lower than that, that's even better. It's worthwhile to note that when engineers talk about reactors where we have nitrate present, but no dissolved oxygen, we call those anoxic reactors. And that's something that biologists and microbiologists typically don't say. They would call that an anaerobic reactor. So when you hear an engineer talk about an anoxic reactor, they're referring to a reactor that has nitrate but does not have dissolved oxygen. Okay, so one factor is dissolved oxygen that we want to minimize for denitrification. Our next factor that we want to think about is pH. And usually denitrifiers prefer a neutral pH. And if we take a look at our balanced biochemical reaction for heterotrophic denitrification, where we have methanol as our electron donor, we can see a little bit about what's happening there. So let's go ahead and write out the whole redox half reaction here for reduction of nitrate. So it's 1/5 of nitrate, right, and 6/5 of a proton and 1 electron, and that's going to go to 1/10 of N2 gas and 3/5 of water. And we've seen this one before. And our accompanying oxidation reaction, we're going to use methanol for this. So we'll see this one a little bit later in our example problems as well. So that looks like 1/6 of methanol, CH3OH, and 1/6 of water. And that's going to go to 1/6 of CO2 and a proton and 1 electron. And when we add those two together, we get our overall reaction looks like 1/5 of nitrate and 1/5 proton and 1/6 methanol. And that's going to go to 1/10 nitrogen gas. Oops, it should be N2 gas. And a super weird fraction, 13/30 water and 1/6 CO2. All right, so you can see in this overall redox reaction, right, that we are actually consuming protons here. And that's important because it means that we're actually generating alkalinity in this denitrification process, which, if we remember back to our nitrification process, this is a critical balance to that, because in nitrification, we're consuming alkalinity. So if we design our system correctly, we can regain some of that alkalinity by denitrification. All right, so our two things that we've seen so far, dissolved oxygen and pH. Our third factor that we're going to take a look at here is our electron donor. This is the third factor that's important for us, and we're going to be talking about mostly organic carbon as our electron donor. Now, there are some organisms that can use ammonia as an electron donor coupled with nitrite as the electron acceptor. We'll talk about that in a different video on anaerobic ammonia oxidation, or anammox. But for now, we're going to look at organic carbon as our electron donor. And this is where your example problem is going to come into play. So there are a whole bunch of different kinds of carbon sources that we can use for this organic carbon. And they can range from things like wastewater. So there's a bunch of organic carbon that comes in with our wastewater, right? It can be things like products from endogenous decay, or decay, So that's products from decay of other organisms. It can be other things like acetate. Methanol is a relatively popular one. And then there are a bunch of proprietary carbon sources that are sold, and these are often some kind of mix of, it could be methanol, ethanol, glycerol, several different things, and they have different benefits and drawbacks to them. So each of these are going to have their own good and bad things to them, and they're going to have different kinetics, and they're going to have, other different properties. And in one of the example problems, you're actually going to look at these three and do a comparison of these three different ones to see which is going to be the most favorable in a system. And that's a pretty typical calculation that you might do if you're working for a consultant or a design engineer trying to determine what is the best electron donor or organic carbon source to use for your denitrification. Okay, so now I have inadvertently written directly over the top of this, so I'm going to end the show for a sec, and I'm just going to move that down. Okay, so now if we look back to our balanced chemical reaction with denitrification for methanol that we just showed in the previous slide, we can use the stoichiometry that's in this, right, that's in this reaction. We can use our stoichiometry Okay, so now that we know that there are all of these different organic carbon compounds that we have, we can use our balanced redox reactions. So this is, again, the balanced redox reaction for denitrification with methanol, we can use that and the stoichiometry from this. So we know we have 1/5 of a molecule of nitrate and 1/6 of methanol. So 1/5 of a mole of nitrate is going to consume 1/6 of a mole of methanol based on the stoichiometry to convert all of that to dinitrogen gas. So we can use this to be able to calculate how much of this methanol we need to denitrify a certain amount of nitrate. And we can do that by starting with these balanced redox reactions. Now, in practice, you're often going to include some kind of safety factors and or consider kinetics and things like that as well. But for the example that we're going to do to compare these three carbon sources, we'll just focus on the stoichiometry. Okay, so that's it for this lecture. We looked at the different factors that affect denitrification, and they include dissolved oxygen, and we want to minimize the amount of dissolved oxygen in our anoxic reactor so that we can maximize denitrification. pH is important. We want to try and maintain a neutral pH, and also it's important to note that denitrification generates alkalinity, which is a good balance for our nitrification process. And then it's also important to understand that we need a sufficient amount of carbon available as our carbon source and our electron donor, specifically when we're talking about heterotrophic denitrification. And so in the next video, we're going to look at a few of our common process flow diagrams that we can use to achieve all of these different things, to tie all of these concepts from our factors that affect denitrification together.